This is the third importance parameter based on the value of the equilibrium constant. That means now you can predict the direction of the chemical reaction. And this is also in your hand. That means you can control the chemical reaction towards the reactant side or towards the product side if you know the direction of the chemical reaction. So here I'm going to discuss the how can you predict the direction of the reaction. That means towards the forward reaction, or it may be a reverse or the backward reaction, or either it is moving to the product side or either it is moving to the reactant side. So this is the direction of the chemical reaction. And again, QC we have discussed during the class. This is the reaction quotient, and it is the ratio of the product divided by the reactant to the power. The coefficients are given in the balanced reaction. And Kc is also the same expression, but the difference is these are without equilibrium concentration. And here T is representing that the concentration was measured at any of the time other than the equilibrium. And here there is no expression as given. It is understood that all these concentrations are the equilibrium. So this will remain the constant. Kc is the constant. That means this reaction is having the equilibrium constant is having the value of the 57 at 700 Kelvin. So let's start. I am going to start with the reaction when the initial concentration of product and reactant are given 0.4, 0.1, 0.2, and when you get the value, this value is 8.0 and it is not 57. That means this is the reaction quotient. So this is the understanding as we have explained in the class. So that means this QC will proceed towards the KC, and when this value will reach the value of 57, then the reaction will remain at the equilibrium. Until then, this will be moving towards the forward side or the backward side, whatever is the condition. When it is reached to the value of the equilibrium constant, that is the condition of the equilibrium. So I am going to explain with the 3 examples over here what would be the condition. The first one is the, let's suppose this is, we are, sorry. We are starting the reaction, and this is the condition 1 when both the QC will be equal to the KC. That means the reactant and the products are at the equilibrium. So this is the condition 1. Actually, at that point, there is no need to discuss because the reactant and product are at equilibrium. That means the reaction is already at equilibrium and the value of the QC will be equal to KC. That means here you can only consider the direction is at equilibrium and the value of it is the K. And again, this is the K product divided by the reactant concentration at equilibrium, and Q is the same expression but at any time or the other than the equilibrium. So what would be the condition? As this is the one of the condition when the value of QC is less than the value of the KC. Again, I am repeating again, this is your target. Any of the value of the equilibrium constant is your target, and this QC has to move towards the value of the KC. And look at this point. That means this is the condition which is given in the previous slide, where the value of QC was less than the value of the KC. And keep in mind, this is the expression. Actually, what would be there maybe you will consider the 2 points, because you have to move towards the equilibrium. One point may be this QC will reach towards the value of this, and this will remain at that point. That means now QC will be equal to the KC, and you will achieve the equilibrium concentration, and then both reactants and products are the equilibrium. And this may be in your mind, why not the value of QC is decreased over here, and then the value of QC decrease, then QC will also be equal to the KC, and then you can also achieve the equilibrium. But this case is not possible. There is only option is available to you. The QC is going to increase to the value of the KC, because this is your target. KC will never decrease. KC is the constant value, and this QC has to be increased up to the level of the KC. And when it is increased, and it is given over here, when the value of QC is increased, there are the option is given over here, the product divided by the concentration. That means when the concentration of product is more and the concentration of reactants are less, then there should be increase in the value of the Q. And this only can be happen if the reactants are converted into the product. So when the reactants are converted into the product, the value of reactants are decreased and the products are increased, and the value of QC will increase. And that means this will reach to that point, and you will get this condition at which the reactants and products are at the equilibrium. So that means if this is the condition, and this condition is only happen when the reaction moving towards the equilibrium side based on the forward reaction. So at that condition, reactants are converted into the product concentration increased and the reactant concentration is decreased, the value is increased, and it will reach that point. And look at this, these are at the equilibrium condition. So the third condition may be when the value of QC is more as compared to the value of the KC. So this is if you have understood this condition, this is also similar to this one, because this is your target, and only the QC is to be decreased up to the level of this one, KC. And this, how can you decrease the value of QC? Opposite to this condition. That means if you increase the concentration of reactant or decrease the concentration of the product, then the value of QC is decreased. And this can only be happened when the products are converted into the reactant, and then the value is decreased. That means when the value of QC is more than the value of KC, the reaction proceeds towards the reactant side or from right to left, and will reach the equilibrium condition. And when the QC is less than the value of KC, then the reaction proceeds towards the forward direction with the increase in concentration of the product and decrease in concentration of the reactant, and this is moving towards the equilibrium. So these three are the example. Based on this one, you can predict the direction of the equilibrium, and this is the conclusion I have explained. Again, QC is less than KC, the reaction is going from left to right, and if it is greater than KC, then it should be from right to left, that means towards the backward side. And if both value are the same, then there is no net reaction occur, that means the reaction is at the equilibrium. So this is all about the predicting the direction of the equilibrium, chemical equilibrium based on the value of the KC.